And this can be done after the key exchange. I mean, Alice and Bob can call each other on a public channel, and they can say, OK, for this bit, I have used this measurement basis. And then they keep all the bits for which they have used the same basis. On the other hand, if they have chosen different bases, they know that their results are not compatible, and they can just discard the bits. Now, if Eve is in the middle, in 50% of the case, she will have to choose a basis. And in all cases, she will have to choose a basis. But in 15% of the case, she will choose the wrong basis. And in that case, she can be detected. Because later on, what Alice and Bob can do is that they can compare few bits for which they have used the same basis. So they know that all the bits should be identical. And if they find difference between the bits, then they will know that there is eavesdropping, and they can interrupt the communication. So it seems to be a perfect world. QKD has been proven unconditionally secure based on the laws of physics. And Eve seemingly has lost the battle against security proof. But there's a catch. There's a catch because those security proof, they're about as good as they can be. I mean, the quantum cryptosystems, they have components. And if you want to build security proof, you have to take models. You have to model the way the components behave. And of course, you have always non-idealities in components. And some of the non-idealities are taken into account into a proof. But as you know, the danger always comes from the unaccounted imperfections and non-idealities. And that's what Eve can actually exploit, the unaccounted imperfections of components, such as the single photon detectors. And that's the one we are going to address now. So yeah, it should be remembered that it's always a perfect world, but for hackers. And that's what this talk aims to illustrate. There's a very general attack to investigate the vulnerabilities of components such as single photon detectors. One such attack is what we call the fake state attack. And basically, it's an intercept-resend attack, which is illustrated here. So we have Alice on the left here. You recognize now Bob's detection apparatus. And Eve is in the middle. And as you can see, Eve has a detection apparatus, which is an exact replica of Bob's. And with that detection apparatus, she intercepts and measures the quantum bits sent by Alice. For instance, on the example here, you can see that you got a click at the detector registering vertical polarization in the horizontal-vertical basis. And then Eve has a fake state generator with which she sends a fake state which ideally should address the exact same detector at Bob's side, while keeping the three other detectors completely blind. So is it possible? Well, if you listen to quantum mechanics, the answer is no, because of the no-cloning theorem. But there are ways around. Let's do now an assumption. What if all those four detectors always click at intensity I0 and never click at intensity I0/2? Then, in the example here, where this detector clicks, corresponding to vertical polarization, Eve can send a fake state with vertical polarization and intensity I0 at this level. So here you have a beam of intensity I0 going, vertical polarization, so the beam is routed here, intensity I0, you get a click, fine. Here, vertical polarization is not transmitted, so you get no intensity here, no click. Now, in the second basis, your vertically polarized photon at the half-wave plate will be rotated to 45 degrees. And then at the PBS, the beam will be split evenly with half the intensity. And in our what-if scenario, those two detectors will not click. So under those assumptions, the quantum cryptosystem using these kinds of detectors are vulnerable. So the question is, are there many single photon detectors working according to our scenario? And the answer is a resounding yes. So let's discuss why. Nowadays, most of the quantum cryptosystems available, they use single photon avalanche diode, SPAD. And that's the one we have been targeting, and we're going to show now that currently none of them is really safe. And the reason basically has to do with the difference between ideal and real. Should always stick to reality. You have an illustration here of the clicks recorded by a detector as a function of the optical illumination at the detector. You see here that you have pretty low intensity level, below picowatts. And we are in the so-called Geiger mode, where we have single photon sensitivity. So you can see there that the detector's count rate increased linearly with the optical illumination, as you would expect from a detector. And ideally, you would like it to go this way, up to higher intensity. But as you can see, below tens of picowatts, the count rate saturates and eventually goes down to exactly 0. So under bright illumination, the avalanche photodiode becomes completely blind to single photons. We can see that you can only start to control the detector just by using bright illumination. So how is that possible? Well, then you have to go into the working mode of the detector. And basically for avalanche photodiodes, you have two working modes, and it depends on the voltage that you apply at those diodes. Above a so-called breakdown voltage in this regime, you are in the regime where you can detect single photon. Basically, the device operates as a trigger device. I mean, a photon arrives, it triggers an avalanche, and the gain is nearly infinite. You record a click. Below breakdown voltage, well, the diode behaves essentially as a mere linear amplifier. That means that the output of the detector is proportional to the light you input in. The gain in that case is much lower than 1000. So if you have just a single photon coming into the detector, this gain is not enough. And to make the detector click, you have no single photon sensitivity. So one question you can ask yourself is, would it be possible that bright illumination bring the SPAD to work from Geiger mode into linear mode, where there is no single photon sensitivity, because that would explain why the detector is blind? And if it's the case, a second question is, if you can bring the detector to work in this regime, is it still possible to make the detector click controllably? And the question, again, is yes. The answer is yes. So let me give an example in a case of a detector for which the avalanche is passively quenched. So what you can see here is the simplified circuit diagram of the detector. So you have the APD here. The APD is biased above breakdown voltage with this power supply. And whenever you have an avalanche, you have a stray capacitance here, which quickly discharge in the APD and into this resistor. And the current at the resistor here is converted into a voltage, which is measured by a comparator. If the voltage goes above the comparator threshold, you get a click. And so under single photon illumination, this is what you can monitor here is the voltage at the APD.